Imagine yourself aboard a spacecraft, drifting through the silent reaches of interstellar space. Outside your window, the stars are ancient, their light having traveled for millions of years just to reach your eyes. Every signal sent by your ship and every maneuver you make requires minutes, hours, or even years to traverse this cosmic void. But then, something impossible happens. A message suddenly flashes onto your screen. It did not arrive via radio waves, nor was it carried by light. It simply appeared, as if its information were woven directly into the very fabric of the quantum landscape. It did not travel here, it simply exists here. This story is a long one, so let us first begin our journey in the realm of dreams, but before we dive in, please remember to like, follow, and share. This is not science fiction, it is the reality of quantum teleportation. In this process, it is not matter that is transported, but information itself. It shatters our traditional understanding of space and time. Unlike the transporters seen in movies, quantum teleportation does not move a person or an object physically, instead, it transmits their quantum state, the fundamental information that defines them. This raises a profound question: if nothing physically moved, how did the information cross the void? To answer this, we must enter the world of quantum mechanics. In this domain, particles can exist in multiple states simultaneously. Entanglement allows distant particles to respond to one another instantaneously, and what we perceive as reality is merely a fragile web of probabilities. This is the story of quantum teleportation, a phenomenon that challenges the very nature of reality and a discovery that could fundamentally transform communication, computation, and our understanding of the universe. But before we reveal the secrets of quantum teleportation, we must first understand the quantum world behind it. Once upon a time, physics was simple. Objects had definite positions, the effects of forces were predictable, and the universe followed clear mechanical laws. This changed with the advent of quantum mechanics, a theory so radical that even Albert Einstein found it difficult to accept, as it overturned our most basic perceptions of reality. At its heart lies a disturbing truth: at the smallest scales, the universe does not have a fixed outcome until we observe it. Imagine a marble rolling on a smooth table. In the classical world, if you know its position and velocity, you can predict exactly where it will be in the next moment. But in the quantum world, this marble has no determined position. Instead, it exists in all possible positions simultaneously. Only when we look at it does it choose a specific location. This is not a mathematical fantasy but a phenomenon confirmed by experiment. Scientists discovered that a single particle could actually interfere with itself, as if it were taking multiple paths at once. The most famous example is the double-slit experiment. When a beam of electrons is fired at a barrier with two narrow slits, a detection screen sits behind it. If electrons were merely particles, they should pass through one slit or the other, leaving two distinct marks on the screen. However, the experiment shows an interference pattern forming on the screen, just as if each electron passed through both slits simultaneously and interfered with itself as a wave. This suggests that before being observed, the electron is not in one place but in all possible places. Yet, the moment a detector is placed at the slits to force an observation, the interference pattern vanishes. In other words, the act of observation itself changes reality. If superposition is strange enough, the next phenomenon is even more bizarre. Imagine two particles originating from the same quantum event. Even if they are separated by kilometers or light years, the moment we measure one, the other instantly knows the result. This is quantum entanglement, a phenomenon Einstein famously dismissed as spooky action at a distance. It implies that no matter how far apart two particles are, they maintain a fundamental connection. If one particle's spin is clockwise, the other must be counterclockwise, and this transfer of information happens without any signaling process. In traditional physics, this is unacceptable because information cannot travel faster than the speed of light. Consequently, Einstein suggested that quantum theory might be incomplete, proposing that particles might possess hidden variables, unobserved properties that predetermine their behavior. In this view, entangled particles were not truly influencing each other but were simply following a prearranged script. This problem haunted the scientific community for decades. Is quantum mechanics purely random, or are there hidden rules? In 1964, physicist John Bell designed a test known as Bell's inequality. Bell established a mathematical limit: if hidden variables truly existed, the measurement results of entangled particles would follow the laws of classical statistics. If quantum mechanics was correct, these results would violate the inequality, showing a non-classical correlation. This theory was eventually tested, and the results consistently showed that Bell's inequality was broken. Quantum entanglement violated classical expectations and could not be explained by hidden variables. This discovery was monumental, meaning the fundamental rules of the universe are not deterministic but probabilistic. A particle's properties are not fixed before measurement, and once measured, the state of an entangled partner responds instantly, regardless of the distance. Imagine a lock safe in front of you containing a letter. You cannot open it, you cannot photocopy it, and you cannot take it out. Yet, you must transmit the complete information of this letter accurately to a friend on the other side of the earth. Not a summary, not a copy, but the original content itself. It sounds impossible, and this is the paradox of quantum teleportation, a method of moving information from one place to another not by sending it, but through erasure and reconstruction. But how does it actually work? It all begins with a quantum state, the core characteristic of a particle that contains all the information defining it. Unlike classical information, quantum information is fragile and limited by the uncertainty principle. For instance, a particle's spin or polarization is not a fixed value but a fluctuating combination of possibilities. If you try to measure it directly, you destroy its original state. Furthermore, unlike a paper document that can be photocopied, quantum information cannot be duplicated. This is the no-cloning theorem, a fundamental principle of quantum mechanics which states that any unknown quantum state cannot be perfectly copied. Once you attempt to copy it, it collapses, and the original information is irrecoverably lost. This poses a problem: if a quantum state cannot be measured or copied, how can it be teleported? The answer lies in the creation of a quantum link. To teleport quantum information, we must establish a deep connection between two distant locations. This is done by generating a pair of entangled particles, two quantum objects whose states are tightly linked regardless of distance. One particle stays with the sender, and the other is sent to the receiver. Even though they are physically separated, they remain part of the same quantum system. Then, a third particle enters the scene, carrying the quantum information we wish to teleport. This particle undergoes a precise quantum operation with the sender's entangled particle, known as a Bell state measurement. At that exact moment, something miraculous happens: the quantum state originally stored in the third particle is completely erased. At the sender's end, that state no longer exists. Simultaneously, the information of that particle is transferred to the receiver's entangled particle. However, the information on the receiver's end is not yet complete, it is in a scrambled state. To recover the original quantum state, one final step is required. The sender must send a piece of classical information consisting of 2 bits of data to tell the receiver how to adjust their particle state. Once these adjustments are made, the receiver's particle becomes a perfect replica of the sender's original particle. It now possesses the destroyed original quantum state, and the teleportation is complete. The most astonishing part of this process is that no physical matter traveled through space. The receiver's particle never touched the original particle, yet it perfectly replicated its quantum information. This raises a fundamental question: where did the information come from? In reality, particle states are not confined to a single fixed location, they are non-local probability patterns distributed across space. In teleportation, the information did not travel, it reorganized, shifting from one particle to another in a way that transcends traditional definitions of space. Another perspective comes from quantum field theory, which suggests that particles are not fundamental units but excitations in a quantum field. If this is true, particle teleportation is not moving something from point A to point B, but rather an operation on the quantum field itself, causing a state to vanish in one location and manifest in another. Regardless of the interpretation, quantum teleportation is not instantaneous communication. It relies on that piece of classical information, the adjustment instruction. This message must still be transmitted via traditional means like light or radio waves, so it cannot exceed the speed of light. While the particle state itself can be teleported instantly, the receiver must wait for the classical information to arrive before they can decode and use it. This limits the use of quantum teleportation. It cannot be used for faster than light communication and does not violate Einstein's relativity. Still, it represents a revolution. In laboratories, scientists have successfully teleported photons, atoms, and even small molecules, with the furthest distance exceeding 1400 kilometers. The future goal is to establish a global quantum network, completely transforming our communication systems. One of the most promising applications of quantum teleportation is quantum cryptography. Since quantum information cannot be copied or stolen without being destroyed, teleportation can be used to establish incredibly secure communication channels. Any attempt at eavesdropping would be immediately detected. In theory, a quantum communication system is unhackable. Beyond security, quantum teleportation plays a critical role in quantum computing. Unlike traditional computers that use bits of 0 or 1, quantum computers use qubits, which can exist in multiple states at once and possess parallel processing capabilities. In solving certain problems, their efficiency far exceeds that of traditional computers. However, building a truly powerful quantum computer faces massive challenges. Quantum states are extremely fragile and easily disturbed by environmental factors like thermal noise or electromagnetic waves. Once interference occurs, entanglement fails, and teleportation is lost. To overcome this, scientists are developing quantum error correction and quantum repeaters. Error correction can detect and fix interference before the information is lost, while repeaters extend the transmission distance of entanglement, ensuring stable teleportation over large areas. As these technologies mature, quantum teleportation could become a standard data transmission method, replacing current encryption and building an uncrackable quantum internet. But the significance of quantum teleportation goes beyond security and efficiency, its impact extends to the entire framework of quantum computing. No matter how fast a classic computer is, it still relies on bits for linear processing. Quantum computers, relying on qubits, can process multiple states simultaneously, giving them an exponential advantage in complex problem solving. Yet, quantum computing faces a core bottleneck, exchanging information between different quantum processors. Since quantum states cannot be copied or read directly, we cannot use traditional methods to transfer the results of a qubit calculation. Here, quantum teleportation becomes the only solution. It allows qubits to be transferred between different processors without being measured, creating an interconnected quantum computing network. This is known as distributed quantum computing, where multiple units work together like a single superbrain. Imagine a world where quantum processors across the globe are linked, performing distributed calculations simultaneously to solve problems traditional computers cannot touch. Molecular simulation would no longer require long experiments but could be used directly for drug development. New materials could be virtually constructed in a quantum environment before being physically manufactured. Artificial intelligence would optimize logistics at quantum speeds, and the accuracy of financial and weather prediction systems would reach unprecedented levels. At the heart of all this is quantum teleportation, the invisible bridge connecting quantum nodes and the key to making the quantum network a reality. Despite this vast potential, quantum teleportation still faces severe technical hurdles. One of the biggest issues is quantum decoherence, the process by which a quantum state loses its characteristics after contact with the environment. Even the slightest disturbance, a change in temperature, an electromagnetic wave, or even a cosmic ray can break entanglement and cause the teleportation to fail. To solve this, scientists are developing a suite of solutions. Some are working on topological qubits, which are more resistant to interference due to their unique mathematical structure. Others are building quantum repeaters to maintain entanglement stability over long distances. While these technologies are still developing, progress is accelerating as governments and private companies invest heavily in the race for quantum leadership. They realize that whoever masters quantum teleportation may achieve dominance in economy and technology. Yet, more than communication or computing, the most profound impact of quantum teleportation might be its challenge to the concept of existence. Some physicists believe that quantum teleportation may reveal the fundamental structure of reality. If information can be transferred without a physical medium, is space itself an illusion? Could quantum teleportation uncover hidden channels connecting distant regions? Furthermore, some speculate that quantum teleportation could be the key to quantum gravity, the ultimate theory unifying Einstein's general relativity with quantum mechanics. Some even imagine a future where humans could achieve a new form of travel, not by moving an object, but by reconstructing it at a distance. Although teleporting a human remains a fantasy for now, the principles of quantum teleportation are already challenging our perceptions of identity, location, and even time. If a particle can be erased in one place and regenerated in another, do we truly exist in a specific location, and how should we redefine the meaning of existence? Quantum teleportation is not just a technological breakthrough, it is a pointer toward the essence of being. It makes us realize that information, rather than matter, might be the most fundamental building block of the universe. The world we live in may not be composed of independent objects, but rather a holistic system of tightly connected information. In such a system, the answers to who I am, where I am, and whether I am still myself may be far more complex than we ever imagined. In quantum teleportation, it is information that is moved, not matter. Atoms do not fly from one place to another, they are destroyed at the source and reconstructed at the destination. For a particle, this is not a problem. But when applied to the human mind, the issue becomes difficult. If we could teleport the quantum states within a human brain, what would happen to human consciousness? Would the reconstructed person still be the original self, or would the original self have effectively vanished? The key lies in the no-cloning theorem. This hard rule of quantum mechanics forbids the copying of an unknown quantum state. This means it is impossible to simply duplicate a person during quantum teleportation. The process must inevitably destroy the original consciousness state to ensure only one version exists in the universe. But what does this destruction actually mean? One view is that consciousness is an information pattern. As long as the neural connections and quantum states in the brain can be reconstructed precisely, the subjective experience of the person should continue seamlessly. It would be like sleeping or being unconscious. The brain state changes, but you are still you when you wake up. From this perspective, teleportation is like walking into one room and stepping out of another. However, this assumption is deeply unsettling because it leads to a terrifying thought: what if the machine scans a person and reconstructs them at a distance, but the original version is not destroyed? If the machine malfunctions and produces a new person while the original remains alive, there would be two identical people with the same memories, personality, and sense of self. At that point, which one is the real original? The concept itself might no longer hold meaning. This thought experiment points to a fundamental problem: identity depends not only on structure but also on continuity. The replica would believe it is me because it has the same memories, but for the original individual, being destroyed might be equivalent to death. Neuroscience offers some insight. Our brains are constantly changing, neurons fire, and connections are formed and broken, yet we still perceive a continuous self. This suggests that the self might not depend on specific atoms, but rather on the patterns of activity within the brain. If quantum teleportation can fully preserve this pattern, then functionally, teleportation is no different from a night of sleep, only the place where you wake up has changed. Yet, there is another possibility. Some theories of consciousness suggest that subjective experience is irreducible, originating from a quantum process in the brain that cannot be replicated. For example, the theory of orchestrated objective reduction suggests that consciousness is not just a computational process but is driven by quantum coherence within the microtubule structures of neurons. If this is true, then even if quantum teleportation successfully replicates behavior and memory, the new version might still lack consciousness. It would speak, walk, and think, but without the subjective feeling of being there, a shell without a soul. Another scenario worth considering is what happens if an error occurs and reconstruction is delayed by 10 minutes. During those 10 minutes, would the individual enter a state of conscious void, or would it be perceived as a momentary jump in time? And if destruction has occurred but reconstruction is never completed, is that equivalent to death, or simply as if one never entered the portal? These questions challenge not only the laws of physics but our very definition of being alive. If quantum teleportation is ever applied to humans, society will have to redefine what it means to be the same person, what continuity is, and what it means to survive. Would the law recognize the teleported you as the original you? Would people be willing to step into a machine that terminates and then reconstructs them, or would they view it as a high-tech form of suicide? This discussion goes far beyond the individual level. It will affect the cognition of human society as a whole. If consciousness can be teleported, can it also be stored? Could we back up a brain state like a file and import it into another body later? Could multiple versions of me exist in different places simultaneously, sharing everything at the start but eventually diverging into different fates and personalities? If these things are True, then teleportation is no longer just a way to move, it becomes a gateway to digital immortality. Perhaps one day, you will find yourself on that spaceship, and the message on the screen will not be a signal from afar, but the data that makes you who you are, ready to be reconstructed at the next star. Imagine a scenario where a quantum teleportation system is activated, and the process is executed flawlessly. A quantum state is destroyed at one location and subsequently reconstructed at another. A person steps into the machine, vanishes, and then reappears at a distant destination. Everything seems perfectly normal. But what if a quantum probabilistic event behaves abnormally, and the original version is not destroyed? What if two identical individuals exist simultaneously, both believing themselves to be the sole original? This is one of the most chilling paradoxes of quantum teleportation. If consciousness is tied to a specific physical structure, then only the reconstructed body is truly you. However, if consciousness is merely an information pattern of quantum states, then both the preserved version and the reconstructed version would believe they are the real me. So, which one is truly you? If both exist, and one of them dies, does the other still represent you? This question points toward a deeper and more provocative concept known as quantum immortality. In certain physical interpretations, a quantum event does not have just one outcome. Instead, it occurs across multiple parallel universes, with every possibility being realized in some branch. From this perspective, consciousness always follows the path where it continues to exist. This implies that no matter how many versions of you meet their end due to an accident, there will always be a version of you that survives. From a first-person perspective, you would never experience death. Instead, you would undergo a series of increasingly improbable survival paths. How would quantum teleportation affect this hypothesis? If the original is destroyed and the reconstruction continues, does that constitute a seamless continuation? If there is even a tiny probability that the original is not destroyed, does it mean the teleporter always survives somewhere? From this angle, every teleportation is not just a move from point A to point B, but a literal splitting of reality. Imagine a future where quantum teleportation is as common as daily commuting. People step into teleportation chambers, intending to move from Tokyo to New York. But in certain branches of reality, the machine malfunctions. One version of you remains at the origin, while another version wakes up in New York. Neither version would be aware of the other's existence until the day you accidentally discover that during a previous mission, the system left behind an unteleported original. Are you still the original you? Do you still believe that only one version of yourself exists? Now, push this problem to the limit. If every teleportation involves destruction and reconstruction, and a person uses the system 10,000 times in their life, have they died 10,000 times? Or is there perhaps a version of you who never used the system at all, remaining in the initial reality, convinced that teleportation technology is nothing more than a scam? Some physicists argue that quantum mechanics does not just describe probability, it describes multiple realities that truly exist. The many worlds interpretation suggests that every event creates a new universe. If there is a probability of failure in teleportation, then a failed version must exist. But from your subjective viewpoint, you will only ever experience the successful outcome. This means even if the success rate is only 1 in a million, you will always find yourself in the world where the teleportation succeeded, while the failed versions, to you, never happened. Yet, because of this, teleportation might be more than a transport tool, it could be a machine that continuously splits reality. Every time it is activated, it erases a version of you in one timeline and reconstructs you in another, all without your knowledge. Imagine if society accepted this view. If clones continued to exist in some branches, would people fear teleportation, worrying that every use is actually a death? Or would society come to accept that individual identity is not a fixed thing, but a constantly shifting, drifting quantum existence? This leads to another question: if consciousness is merely a state of information, does teleportation truly preserve consciousness, or does it only preserve memory and behavior? If memories can be copied but the subjective experience cannot be transferred, then the new version might be nothing more than an empty shell that looks like you. More complex is the issue of probability. If every teleportation introduces subtle differences, would you eventually become a different person over a long period? Is there a form of conscious drift where your memories and personality gradually change through multiple teleportations without you ever noticing? There are even more frightening possibilities. What if a quantum teleportation system could be hacked or manipulated? If someone tampers with the data during the process, would you still be you when you arrive? Could your memories be altered or your personality reshaped? In an extreme scenario, if a system deliberately created multiple versions of you, each clone believing itself to be the only one, they would quickly diverge into different fates. Who then has the right to say, "I am the real me"? If consciousness is just an information pattern, then all these copies are real versions of you. But if identity requires a deeper subjective continuity, then this process may have already exceeded our understanding of existence. Does quantum teleportation hold the key to the nature of time? It has already challenged our perception of space. Teleportation suggests that distance might be an illusion, as information does not need to traverse the space between 2 points, it can simply appear in another location. If space is not an obstacle, perhaps time is not what we think it is either. We know that quantum teleportation does not move physical objects, it moves quantum states, the essence of a system. This is possible because of quantum entanglement, where two particles form a link that transcends distance. When one changes, the other responds instantly. This reaction does not travel via traditional signals, it surpasses spatial limits. But what if it also surpasses the limits of time? In fact, quantum mechanics has long hinted that time does not flow in a clear, sequential order as it does in classical physics. In the quantum world, the boundaries between past, present, and future become blurred. Some theories propose that entanglement acts not only across space but also across time. If true, this means teleportation could involve different points in time. One experiment, known as the delayed choice quantum eraser, presents the shocking idea that quantum events are not finalized until they are observed, and their final state can be influenced by decisions made after the fact. In other words, a choice you make now could change something that has already happened. If quantum teleportation is built on such a mechanism, could it be used to transmit information across time? A key concept here is entanglement swapping. In current experiments, we use entangled particles to relay information. But what happens if those particles are entangled across different points in time rather than different points in space? Imagine a scientist on Earth creating a pair of entangled particles. He sends one into deep space and keeps the other on Earth. Decades later, the particle in space is used for a teleportation experiment. Despite the passage of decades, the entanglement between the two remains unbroken. When the scientist manipulates the particle on Earth, the distant particle reacts instantly, as if information traveled through time from the present back to the past. This raises a question: did the information actually travel through time, or is time simply not a constraint in this process? Some physicists believe that if we can precisely control entangled states, we might build a communication system that is independent of time. Theoretically, information could be received before it is even sent, shattering our understanding of causality. History would no longer be a linear track moving only forward, but a structure that can be adjusted, fed back into, or even looped. Furthermore, there is a cosmic mystery closely related to time, the black hole. Black holes have long been seen as entities that challenge the structure of time. Traditional views suggested that anything falling into a black hole is lost forever, but modern physics argues that information cannot be destroyed. Some theories suggest that black holes do not swallow information but instead use quantum entanglement to teleport it to other regions of the universe or even to different moments in time. This strengthens the link between time and teleportation. Another clue comes from closed time-like curves in general relativity, which allow objects to return to the past, forming a time loop. If quantum teleportation could be combined with such a structure, we might send quantum states into the past without violating known physical laws. Unlike traditional time travel fantasies, this would not involve a physical body traveling, but only pure information, thereby avoiding classical paradoxes like the grandfather paradox. But this leads to a serious problem: if we can send information to the past, can we change history? Could we warn ourselves of a disaster so that it never happens? Or would the universe prevent such an act? Scientists have proposed the self-consistency principle, suggesting that even if time can be manipulated, the universe will adjust itself to ensure no contradictory history occurs. Thus, even if we successfully teleport information, we might only be sending messages that were always meant to be received, without changing the established timeline. A more radical explanation suggests that teleported information does not change the original history but opens a new timeline entirely. This is the many worlds interpretation again, where every event splits a branch in the universe. Sending information to the past would not modify our current reality but would allow another version of history to unfold in a new universe. This means your original timeline remains unchanged, but another timeline is rewritten, and you would never know if it happened. It is like opening a door between countless parallel worlds. Teleportation becomes a navigator of time, guiding us to choose different versions of history. Some theories go even further, suggesting that our consciousness might be constantly performing time jumps. Instead of the body moving, quantum processes in the brain might be constantly shifting between future possibilities. Certain theories of quantum cognition propose that our choices are actually selections from multiple futures. Could this explain intuition, premonitions, or even the experience of déjà vu? People often say they feel as if they have experienced something before. Perhaps that is the brain capturing a quantum echo from the future. While these ideas remain speculative, one thing is clear: the transmission of information does not always follow classical physics. The next step is to determine if time is a dimension we can navigate freely. If it is, then quantum teleportation will not only bridge space but may help us truly understand the essence of time itself. The most profound hypothesis brought by quantum teleportation is that information might not be limited by space at all. If information can move instantly between two locations without crossing the space between them, does this hint at a greater truth? Perhaps the entire universe is an invisible teleportation network. In our eyes, the universe is a continuous space, a vast expanse dotted with galaxies and stars. But at the quantum scale, space might not be continuous. It may be a web supported by hidden connections, where the distances we see are merely an appearance. A growing perspective in modern physics suggests that space is not the fundamental structure of the universe but an emergent byproduct of quantum entanglement. In other words, the universe does not have entanglement happening within space, rather, the sense of space itself is created by entanglement. If this is true, then quantum teleportation is not just a strange quantum phenomenon, but a direct way of interacting with the very architecture of the universe. We can compare the universe to a neural network, where nodes are connected not by wires but by information itself. In such a network, the shortest path between 2 points is not necessarily a straight line, but the channel with the least informational resistance. If the universe operates this way, then quantum teleportation is not crossing space, it is revealing that space was already connected in ways we cannot perceive. This would overturn our entire understanding of distance. Information does not need to propagate through space because all points are already linked, and what we call movement is merely a transformation in how we connect to the universe. This view aligns with the holographic principle, a radical but increasingly respected theory. According to this principle, our three-dimensional world may be a projection of information encoded on a lower dimensional boundary. If this is true, every quantum teleportation is a direct operation on that hidden dimension. This also makes us re-examine the role of black holes. Rather than being endpoints, they might be ultimate terminals for information, potentially teleporting it to the other side of the universe or even to another universe entirely. This leads to the speculation that the interiors of black holes might be connected to wormholes, also known as Einstein-Rosen bridges. If these ideas hold, then quantum teleportation is not just a small lab experiment, it is a mechanism that has been running since the birth of the universe. If entangled particles can link across the cosmos, then entanglement chains might exist between black holes and distant stellar regions, forming an information teleportation network for the entire universe. From this perspective, quantum teleportation is a microcosm of how the whole universe operates. Think about unsolved astronomical mysteries like fast radio bursts, which come from billions of light-years away with staggering regularity. Are they natural teleportation events? Or ultra-high-energy cosmic rays that possess energy far beyond theoretical limits? How do they cross space to reach Earth? If space is an entanglement network, we might say these particles simply jumped. If entanglement exists not only within our universe, but is a fundamental property across universes, then quantum teleportation could be a gateway between multiple realities. In the quantum realm, particles have no determined state, they exist in all possibilities until measured. Every choice we make might lead to a future that truly exists in a different universe. If we can manipulate the state of particles through teleportation, can we choose which version of reality we inhabit? This would mean we are not just moving information, but choosing which branch of the universe to access. Furthermore, is our consciousness related to this? If thinking involves quantum mechanisms, consciousness might occasionally jump. Human intuition, sudden inspiration, or premonitions might be the brain temporarily connecting to a cosmic entanglement structure, grabbing a piece of information from another future. Some even suggest that quantum teleportation is not a future technology but an ability we have forgotten. Perhaps ancient civilizations or extraterrestrial life have already mastered it? Could this explain unidentified flying objects that move, turn, and vanish instantly, violating known laws of physics yet appearing as if they never traveled through space? Are they using a cosmic-level teleportation protocol? If the universe is not an empty space but an invisible network of entanglement, then quantum teleportation is no longer a technological miracle, it is part of the essence of reality. Our future may not lie in building faster spaceships, but in learning to use the connections that already exist. That would mean leaping between galaxies, navigating between realities, and reshaping existence between consciousness and information. If the universe is truly a teleportation network, then every one of us is not just a traveler in space, but a connector. From the moment the universe was born, we have been linked within this vast and profound web. For decades, the scientific community viewed quantum teleportation as a mere laboratory curiosity, a precise demonstration of quantum mechanics that seemed far removed from our daily lives. It lived in academic papers, on whiteboards, and within the realms of science fiction. But now, quantum teleportation is stepping out of the theoretical shadows and into the real world. Governments, tech giants, and elite research institutions are racing to build practical systems, desperate to harness this power because it has the potential to reshape communication, revolutionize computation, and overturn our very understanding of the universe. The most immediate and revolutionary application is in the field of quantum communication. Today, every piece of data we send, whether it is a phone call, a financial transaction, or a state secret, relies on traditional encryption. However, all classical encryption methods are essentially temporary. Given enough time and computational power, even the strongest codes can be broken by a classical computer. Quantum teleportation ends this vulnerability. Its core capability is the ability to transfer information without transmitting any physical particles. In the realm of communication, this enables quantum key distribution. Encryption keys are not sent through a fiber optic cable, instead, they are generated through quantum teleportation. If an intruder attempts to intercept the information, the quantum state immediately collapses, and the system detects the anomaly, instantly cutting the transmission. Eavesdropping becomes physically impossible because the act of listening itself alters the content of the transmission. China has already taken a pioneering lead in this race. In 2017, Chinese scientists successfully achieved quantum teleportation from the ground to a satellite over a distance exceeding 1,400 kilometers, marking the furthest record in human history. This satellite, named Messias, was used to establish an intercontinental encrypted communication channel, proving to the world that quantum teleportation is not a dream but the blueprint for a future internet. This new network will be unhackable, untamperable, and impossible to forge. The significance of quantum teleportation, however, goes beyond mere security. It promises unprecedented leaps in speed and efficiency. The current foundations of our internet depend on fiber optics, radio waves, and undersea cables, structures limited by physical interference, signal decay, and a speed that can never exceed that of light. A quantum network would bypass these bottlenecks, achieving perfect fidelity over long distances without the fear of packet loss, hijacking, or latency. This represents a fundamental paradigm shift in how we connect. Yet, this is only the beginning. Quantum teleportation will also be the key to building the next generation of supercomputers. Traditional computers, no matter how powerful, are based on classical bits of zeros and ones, processing information sequentially. Quantum computers use qubits, which can exist in multiple states simultaneously, theoretically allowing for an exponential acceleration of complex tasks. But to achieve truly large-scale quantum computing, we must solve a massive problem: how to make multiple quantum processors work together in a stable, collaborative way. Because quantum states cannot be read or copied, traditional methods cannot be used to pass the results of a calculation from one processor to another. In this context, quantum teleportation becomes the only viable bridge. It can move the computational state of a qubit directly to another processor without measuring it, thereby creating a truly interconnected quantum computing network. This architecture is known as distributed quantum computing. Its vision is for quantum units across the globe to collaborate synchronously, solving massive problems like protein folding, financial simulations, and climate forecasting in a fraction of the time it takes today. It will accelerate drug design, optimize global logistics, and drive breakthroughs in artificial intelligence. The key to all of this is the efficient teleportation of quantum information. Challenges still remain, of course. The most stubborn hurdle is quantum decoherence, where even the slightest thermal noise or electromagnetic interference can cause a quantum state to lose its entanglement, resulting in a failed teleportation. To combat this, researchers are developing a range of solutions, including quantum error correction to detect and fix information anomalies, and topological qubits, which are structurally more stable and resistant to interference. They are also working on quantum repeaters to extend the distance of entanglement transmission and build a wide-area quantum network. There is also the issue of scalability. While we can currently teleport individual particles with stability, building a global network requires the simultaneous teleportation of massive groups of qubits. This presents a titanic challenge for laboratory precision, environmental stability, and engineering. Despite these obstacles, progress is accelerating. Nations are pouring billions of dollars into the field to secure a foothold in quantum technology, realizing that whoever masters it will hold a decisive advantage in the future of economics, defense, and science. Beyond the technical, we also face a profound philosophical challenge. If information can be teleported without a physical medium, does it mean that space itself is merely an illusion? If a particle can be destroyed and then reborn at a distance, what is the meaning of existence? Quantum teleportation is more than a scientific breakthrough, it is a crack in the door that lets us glimpse the other side of reality. It reminds us that the essence of the universe is not matter, but information. Things are not as separate as they appear, they are deeply and fundamentally connected. Where I am, who I am, and whether I truly exist, all of these concepts may need to be redefined. We do not yet know exactly what the future looks like, but one thing is certain: quantum teleportation is no longer just a theory. It is happening, and it brings not just a technological revolution, but a complete reconstruction of our reality. That concludes our discussion for today. I hope you have a beautiful dream, and I will see you in our next episode.